Okay, so next we need to talk about something that's called fields. Now I actually mentioned them in the gravitational unit. A field, and there's different types, it's not the place where like Bambi eats the wildflowers while, playing with its little friends. A field in physics is an area around an object where a second object experiences a force from the first one. So when we talked about fields in the gravitational unit, it was a gravitational field. And if this was the Earth and this was the moon, we said the moon was in the Earth's gravitational field. The moon was in that area around the Earth where if any object enters that area, it's going to experience a force pulling it towards the Earth. If you put a little jetpack on your back and you zoomed up into the air, you should be able to imagine that as you moved up further and further and further away from the Earth, the pull of the Earth would be getting weaker. Well, what we're saying is then that as you move away from an object, the field of that object gets weaker. So the gravitational field of the Earth is the area around the Earth where any other object with mass will experience a force being drawn into the central object. So here, the Earth is the central object that's creating the field, and the moon, or any of us, are an object that's in the Earth's field that's experiencing the force. And so we also found an equation for the strength of the gravitational field. The strength of the gravitational field is just little g. And we actually have two equations for it. Fg divided by m, or G equals Gm over r squared. This m is you and I. It's the object brought into the field. This m in this equation is the object creating the field. That's the mass of the Earth in the example here. So it's the object creating the field. Okay? So you've already met a gravitational field, but there are other fields. There are fields around charged objects. Okay, so I'm going to make this one a positive just because I want to. And you should be able to imagine that if I bring another charged object anywhere near this object, that charged object's going to experience a force because of this central one. And that force will be an electrostatic force. So we say every charged object has an electric field around it, just like every object with a mass has a gravitational field around it. And if you're lucky enough to have taken Science 12-2, then you would have learned that any magnetic object has a magnetic field around it. And they all act the same, okay? They all act the same in the sense that the further you get from the field, the weaker they are, that they apply a force on the other object that has a certain characteristic. So in this case, for the gravitational field, the characteristic is it has to have mass. In the case for the electric field, the characteristic is that it has to have a charge. Now we can show the strength of a field by something that's called, I'll come back to the electric one in a minute, by something that's called field, whoops, that's not an F, field lines. It's supposed to be an F. There we go, now it's an F. Okay? Field lines. And field lines are lines that show the strength of a field. They're lines that show the direction of the force at any given point in the field. So up here, this little arrow that's coming from the moon towards the Earth, that's a field line. And if the moon was here, then the field line would be going in like this. And if it was here, it'd be going in like this. And so we draw the field lines. If we were to draw the gravitational field lines around the Earth, they would all be going in this way. Now, there's a few rules for field lines. One of them is they never cross. And they don't cross because they show the direction of the force at any given point in the field. And if they crossed, it would mean that a force was going in two directions at once. And nothing, not even a force, can go in two directions at once. Another fact about field lines is that the closer they are together, the stronger the field is. So look here, right, close to the surface of the earth, these field lines coming in, and it doesn't matter if I draw another 20 in here, they're still going to be closer together near this surface of the earth and spread apart as they come out. So the closer the field lines are together, the stronger the field. Okay? All right, so field lines, fields. So now let's go back to electric fields. So for electric fields then, here's my positive charge. And if I have another little tiny positive charge out here, then I can figure out that what the direction of the field lines would look like, right? This positive is not going to like this, the one that's setting up the field is not going to like the one I'm bringing in. And so it's going to push it away. Like this, right? No matter where I put the positive around this central guy, it's going to push the little positive away. Okay? So the field lines around a positive charge, the central charge, are always going outward. Now you might say, but wait, what if I put a negative there? Well, that was a problem back 200 years ago when they were discovering all this, and they said, wait, won't these field lines change direction depending on if I have a positive charge here or a negative charge out here that I'm bringing in? And so the scientists at the time got together and they said, no, we will always define the direction of the field lines around a charged particle as the direction of the force that would be put on a tiny positive charge being brought into that field. And you could think of this tiny positive charge as if it's like your little kid brother or sister or cousin, right? They're tiny and they're always positive. Like, you want to go to the store with me? Yeah, yeah, yeah. Want to go watch TV with me? Yeah, yeah, yeah. Want to go jump off the roof with me? Yeah, yeah, yeah. Like, they're always positive. And so this little guy is too. And really, we use him then to figure out the nature of the central charge. We toss him into a field and we see what happens to him. And depending on what happens to him, that tells us the nature of the charge setting up the field. You've probably done exactly the same thing with that kid, brother, sister, little cousin. You probably sent them into your parents and said, go suggest to mom and dad we go out for pizza. Right? You're using them as it's called a test charge. You're using them as a test charge to see the nature of your parents. All right, so we need an equation. The great news is the equation's going to look exactly the same as the gravitational ones. The letter for electric field is a capital E. Okay? And capital E then, if it's going to look exactly like this, should be, because remember we had Fg is equal to GMM over R squared. Okay, so, and we have Fq is equal to KQQ over R squared. So so they're totally parallel. Well, these guys are too. Capital E then will be equal to Fq instead of Fg, and instead of the mass, it's the charge of the object that's important. So one of our equations for electric field is this. The other one is exactly like the second one over here, right? This one over here, watch my time, this one over here is just this piece. Well, and so is this one, right? Because if I put in here KQQ over R squared and divide it by Q, one Q is going to cancel, and I'm going to have KQ over R squared, my second equation. The Q on the bottom, the charge brought into the field. The Q on the top, the charge creating the field. Identical to gravity. So in the next video, we'll talk about, we'll come back to these and we'll talk about directions. Tonight, your homework's with forces, your practice questions. Tomorrow, they'll be with these after we get the directions straight. Okay?